Hi guys, this is Michael. Today let's look at the problems that the Lintcode problem number 114, unique passive. This problem is about dynamic programming. Let's look at this problem description first. It is about a robot is located on the top left corner of the n by n grade. The robot can only just move to either down or right at any point in the time. The robot is trying to reach the bottom right corner of the grid. So problem is that how many possible unique passes are there? So like I mentioned, we're going to just use the dynamic programming to resolve this problem. Why is that? Because usually, if you find some keywords, like how many passes, how many solutions are there, usually, based on the experience that you can use the dynamic programming, because problem does not, require us to give out each possible solutions. The problem just require a number, how many possible solutions are there. So let's see how we can do it using dynamic programming. Typically speaking, if you want to resolve it using dynamic programming, then you need to complete 4 steps or answer 4 questions. If you can just answer all of them, that means you're good to go. The first question is here. I have notes here. Is definition. Because if you want to use a DP, dynamic programming, you usually have to define a DP array. So sometimes this DP array is 1 dimension. It can be DPI, or it can be 2 dimension, DPIJ, sometimes even more dimension. So based on your definition, your dynamic programming will be different. In this case, we're going to just use 2 dimensions DPIJ because the problem is it is about the 2-dimensional grade. So we use DPIJ. So we need to give the definition of the DPIJ. Usually, if you use the DP approach, the definition part is quite need some aspirations. If you can give a good definition, you can just resolve this faster. If you give a bad definition, you probably need to do more steps. So in our case, we define DPIJ as this. DPIJ means the total possible passes that the robot starts from the starting point, which is the top left corner. We call it 0, 0 to move to point ij. That's what DPIJ means. Okay, so you got that right. The second, we need to describe our answer. So what is our answer? Our answer is we need to know that when the robot reaches to the bottom right corner of the grid, we need to know that how many passes, are there. So based on our first, DPIJ definition, so our answer should be DP n minus 1, m minus 1, and n minus 1. That makes sense, right? That means that the robot starts from 0, 0 to move to the top right corner, and how many passes are there. That's what we want. So our answer, the solution what we're looking for, is totally consistent with the definition. So this is very nice. So third questions we need to answer, we need to figure out is what is the transfer equation, or I should just say state transfer equation. So dynamic programming, this approach actually is a way to study the state, adjacent state, the relationship of the adjacent states. If you can figure out a way to describe the relationships, that is, you can find a state transfer equations, then that means you have a chance to calculate all of the states, because eventually our answer is one of the state. So, state actually we need to figure out what is the relationships between DPIJ and its previous state. So in this case, we realize that DPIJ is related to dpi minus 1j and dpi j minus 1. So why is that? Because when the robot reaches to the point ij, right, it can get, because the problem tells us the robot can only just move down or move right. So when the robot reaches to ij, it could be from the I minus 1 j, which is could be from the left, or it could be from the upper point dpi j minus 1. And how many ways, how many unique passes this dpi minus j has, and plus the dpi j minus 1, and that is the the answer of the dpij. So third step is done. So last step is that we need to give the initialization, because when we do the state transfer equations, this is two-dimensionally, and we need to represent dpij using previous states. So in order to resolve all of these states, we need to give the proper initializations. So this part actually, usually we just initialize the first line, first row, and first column. This is all by experience. That's the way how DP works. You can just memorize that in heart. When you try to resolve the DP, you just always try to initialize the first row and first column. In most cases, that works. So let's say first row. We use the DPI 0. That means for the this is first column. For any point in that first column, we realize that actually their unique passes is 1, right? Because like this problem describes that a robot can only just move down or move right. If you are at the very left column, you can only just the robot can only come from the top, about one. So the unique passes is 1. So similarly, if the first row is 1, yeah. So this two just basically initialize the first row and the first column, which is column row 0 and column 0. So once this is done, and we successfully completed 4 tasks, and we're good to go. So let's see how we program this. So unique passes is the entrance of this problem, and first we need to initialize the DP. As we mentioned, the DP is 2-dimensional, so we need to initialize the n by n size of this DP. We just initialize every value to be 0 in this array. I use the least comprehension Python syntax. For we just loops through all the rows. We have m rows, and for each row we generate a list. It is the 0, and we just multiply by n, then we generate a list of n zeros. Alright, so this is done, and this part is the initialization part. We just initialize the column 0, initialize the row 0, and initialization is done. And the third part is like a template. In most cases, DP we just use the 2 nested for loops to resolve the issue, because we already initialized the row 1 and column 1. So here we just the row just starts from 1 and column just starts from 1, and we actually just put our state transfer equations here. That's what we figured out in steps 3. So once we put it here, once this for loop finish the execution, we realize that based on the initialization values, based on this state transfer equations, and all of the DP values will be calculated, and our answer is the one of the state, which is return one of the state. Then done. That's how we resolve the whole question. So let's test this one. Submit the code. It's compiling. It's running. So it looks like so far so good. So yeah, thanks for watching. This is today's algorithm. So definitely just take some time to think about these 4 steps. All right, thank you so much, and bye-bye.